Alright everyone, we're going to go ahead and get started with this version of the video. Pointing out a couple of things as we go. Parts of it are going to just be review of previous topics when we talked about bonding, and parts of it will be somewhat new. Starting off with the old stuff. Now, when we look at the term chemical bond, we remember that we are looking at a very complex or difficult term. Not necessarily difficult to understand, but there's so many aspects to it that it can sometimes become confusing. Now, usually the general definition that we're going to use is it's going to be the forces that hold a group of atoms together to make a functional unit, a compound, a molecule. Now, a bond will form if the energy of the aggregate is lower than the separated atoms. What does that mean? Well, when we have these atoms apart, each of them has a certain amount of energy, but there's still some attraction that's going to happen based on the nucleus. That's what we're seeing in the diagram here. As they get closer and closer, they become closer and closer attracted, and to the point where they actually form a bond. Now, this bond is going to be the best distance between the nucleus. Why do I say between the nuclei? Well, if the nuclei get too close together, we're actually going to end up with them repelling each other. Also, while they're close, you notice we have these electrons or the electron moving around if we're looking at this as a hydrogen atom. During that time where it's moving around, it also has the opportunity to repel the other electron coming from the other hydrogen. This is going to give us a better picture of how this is going to work in terms of bonding. So, far apart, there's a certain amount of energy. We usually say 0, but since we're looking at potential energy, the closer that they get together, we find that the energy drops. Now, if it goes any closer than that optimum distance, then you notice that the energy begins to go back up. That's what we're noticing here, that we end up back up above 0. Whereas when they're at that optimum distance, in this case, in terms of nanometers, 0.074 nanometers, it's the optimum distance and it's lower in energy, making it easier to form that bond. Now, three main ideas that we talked about are two main that we're going to talk about. Ionic bonding is where we're going to actually transfer electrons, and covalent where we're actually going to share them equally. Now, what about those that are in between? Those are the ones that we call polar covalent bonds. These are going to be characterized by unequal sharing of the electrons between the two atoms in the molecule. Now, because of this, we're going to end up with that slightly positive and slightly negative symbol that we talked about before. Okay, partial positive, partial negative. Now, if I have this molecule, HF, because of the fact that this is going to be a polar molecule formed because of the high electronegativity value of fluorine, it's going to cause the electrons from the hydrogen to actually be pulled a little bit closer towards the fluorine. This gives it that partial negative, partial positive charge. When I turn on the electrical field, we note that, hey, the partial positive are attracted towards the negative charge, whereas the partial negative are attracted towards the positive charge. Now, electronegativity is the main thing that plays the biggest role here. It's the ability of an atom and a molecule to attract shared electrons to itself. So, when we have our example like we had here, these two are actually sharing electrons. They form a covalent bond. But because of the fact that the electronegativity value of fluorine is so high, it actually is strong enough to pull the electron further away from the nucleus of the hydrogen. Now, when we compare the electronegativity values for each of the intended atoms that are going to bond, we actually come across with whether it be polar, nonpolar, or even ionic if the difference is so high. On the periodic table, it usually decreases as we go from from the top to the bottom. It decreases, and as we go from left to right, it increases, with the highest value being 4, which we use for fluorine, and the lowest value being cesium, which is 0.7. And this is just a little guide. And we usually use the Pauling scale. That's the one that you're going to be most familiar with as we continue. Now, the more covalent in character, the closer those values are actually going to be. So the closer they are to 0, the more covalent it's going to be, meaning nonpolar. But as we continue to get the distance further and further away from 0, we get towards the polar covalent compounds, and even where the difference is very large, towards the ionic. And this is why we form those ionic compounds when it comes to metals and nonmetals. Look at the values of the metals versus those of the nonmetals. There's a big difference, and in that big difference, we get the different bonding orders. Now, dipole moments. The property of a molecule whose charge distribution can be represented by a center of positive charge and a center of a negative charge. Simplified terms. If I have a molecule, some of these molecules are going to be partially positive, partially negative. We get that, and we talked about the fact that we'll have these polar bonds. But the overall molecule does not necessarily have to be positive, partially negative. If we can find a way to, and it says we can draw the arrow that points towards a negative charge center with the tail end indicating the positive charge. If we can get all those pointing in one direction, usually that indicates that we actually have a polar bond, and it's going to exhibit what we call a dipole moment. So looking at the example we have here of water, we have our oxygen atom, which has a higher electronegativity than hydrogen, so it's going to pull the electrons in this direction, partially positive on both of those ends, two partially negative. Now, notice that the center of my negative is all on one side. This is telling me that I'm actually exhibiting what we call a dipole moment. And this is that's showing based on the electronegativity map, which is also found in your textbook in section 8.3. Now, imagine we have something where we can't necessarily do that. In this case, we're using carbon dioxide as our guide. Well, we have polar bonds that are happening here. The electrons are being pulled outward towards each of the oxygen. Now, because of the fact that they're being pulled outward, they're being pulled in two separate directions. Those separate directions are actually going to cause us to end up with what we call no net dipole moment. There's no way that I can split it so that I can get just my negative on one side, my positive on one side. And we can see this even by the electron density. This meaning that even though it is a polar, it contains polar bonds, it is a nonpolar molecule. And this goes back to the FRQ that we had in class the other day. Now, when we think of something being stable, it's usually going to be based on the noble gas configuration. We talked about electron configurations before. Each of the atoms wants to have that stable electron configuration for the noble gases. So it's going to do whatever it needs to do in order to form that. When two nonmetals react, they form a covalent bond, which means they end up with the electron configuration for both atoms. Both of them are going to end up with the noble gas configuration. But when we do this to form an ionic bond, we're actually going to transfer electrons away. And this is going to help us to mimic the valence orbitals for each of our noble gases. Now, because of this fact, this is actually going to allow us to predict a couple of things. One, ionic size. Two, atomic size, ionization energy, and electronegativity. We use this information as we proceed forward to actually understand how polar a molecule is going to be, or how nonpolar it's actually going to be, and be able to rank those different things as we continue to go. Now, we're actually going to stop here for this first video. Take your time, review, look at the notes in the PowerPoint that I gave you. Take your own notes as you're going through this, and hopefully we can get it all to make sense. And I'll see you in class.